and welcome. Good morning, or almost afternoon. I'm Lloyd Minor, Dean of the Stanford School of Medicine, and it's wonderful to see you all here today. Our aspirations start right here in our community. We're committed to being the very best neighbor we can be to the people in Northern California, you, our neighbors. To be the place where all of you turn when you need the services that we offer. That's medical care, and it's also information and resources. Days like today for the benefit of you and your families. So let's turn our attention now to our next very exciting offering, the vision of our keynote speaker, Siddhartha Mukherjee. You may know him as a Pulitzer Prize-winning author of The Emperor of All Maladies, a biography of cancer. He called his own work a biography, but if you read it, you know that it reads like a page-turning thriller about the history of cancer and its impacts on society. We like to claim Dr. Mukherjee as one of our own because he received his undergraduate degree here at Stanford and worked in the laboratory of Nobel laureate Paul Berg, defining the genes that change the behavior of cancer cells. From Stanford, it was on to Oxford with a Rhodes Scholarship, and then to Harvard Medical School. Today, he's an assistant professor of medicine at Columbia University, where he pursues medical research into the origins and interventions for blood cancers. He also continues to treat patients as a cancer physician. All of this while writing a Pulitzer Prize-winning book. Of his book, his publisher says that Dr. Mukherjee examines cancer with a cellular biologist's precision, a historian's perspective, and a biographer's passion. And next year, you'll be able to watch a Ken Burns documentary based upon The Emperor of All Maladies, scheduled to air on PBS. Today, he'll share with us his view of this disease and his vision for the future. After his remarks, my colleague, Amir Dan Rubin, CEO and president of Stanford Hospital and Clinics, will conduct a session in which you can ask questions. So be thinking about what you want to ask. And now it's my great privilege and honor to introduce Dr. Siddhartha Mukherjee, who will deliver the talk. Thank you very much.
Thank you so much. It's an incredible honor being here. I like to say that I'm one of the children of this auditorium because this is a place named after Paul Berg, my undergraduate mentor who I had dinner with yesterday. And for me, it's also a very important place, historically, geographically, a very important place because when I trained here, I saw in a room not far from here the very first child that I would encounter who received chemotherapy and was cured of leukemia. And then a few months later, in a room just a few doors away, the very first woman I saw die of breast cancer. And those two poles represented to me as an undergraduate the incredible work that had been achieved, the incredible achievements of medical sciences through the passion of very, very dedicated physicians and researchers, and also the long journey ahead that will change, hopefully, the landscape of cancer as we move forward. The question that I want to answer and ask first, the question that I want to ask is a question that I think is on everyone's minds, which is, where are we? How did we get here? And what happens next? It's a question that we really need to ask as a community, as a society, to figure out what the next steps are in a disease that has simultaneously been thwarted by us in several important instances, but also continues to escape from our grasp over and over again. And it requires, I think, as everyone here knows, it requires a kind of continual evaluation. I think we shouldn't make a mistake. Cancer is by far one of the most significant human challenges in our history, bar none. And I think that it demands a kind of ingenuity, which we have, but it demands it constantly. It demands it in a way that we can't give up at one instance, because it is, as I describe in my book, I call it a Red Queen's race. You know, there's a very famous scene which I enjoyed from reading Lewis Carroll's books. And the Red Queen says in the middle, Alice runs up to the Red Queen and says, "Why are you running?" And the Red Queen says, "Well, I'm running because the world is moving with equal and opposite ferocity in the other direction. I'm running just to keep in place." So cancer demands that kind of running. It demands that kind of running, and ultimately it demands that kind of running so that we are not in place, but in fact are moving forward. But even maintaining our knowledge around cancer, even maintaining what we know today, requires a kind of a deep commitment, a deep effort. And one of the sort of central messages of my talk is that we need to double that effort. That effort needs to be doubled because it is with us, it's amongst us, and unless we generate a next series of innovative advances, we will be left behind. The Red Queen will be falling behind in this race. So what I thought I would do today in service of those questions, where are we today, what has happened, what does the landscape look like, what is the global view? I thought I would take you a little bit through the history or through the past because it informs us about how we got here and what happens next. And I like to think about cancer. You know, the landscape of cancer is often, it often feels like losing the forest for the trees. You know, you read a newspaper and someone says, you know, what a wonderful advance happened yesterday. So you pick up the next newspaper and you say, clinical trial fails. The third article in the same newspaper says, important advance against breast cancer. And you feel as if there are so many trees that you begin to lose the forest. What does the forest look like? What does the landscape look like? So I thought I would take a bird's eye view, as it were, and then zoom down on individual changes in cancer treatment and prevention. And if you take that bird's eye view, I like to think about cancer in terms of essentially four revolutions. Not 1,000, not 300, but 4 revolutions. And these 4 revolutions, we're in the middle of the 4th. These 4 revolutions, I think, have redefined the way we think about the treatment and prevention of cancer. And when we think forward, I think we need to go back to reimagine these 4 structural revolutions, as it were, in cancer. So I'm going to start with my first slide. I want you that. It's right here. Long before that very first revolution arrived, there was a long history that predated it. Cancer is thought about as a modern disease, but in fact, it is an ancient disease, probably one of the most ancient diseases we know. This is a picture of one of the first medical documents that we possess as humans, the Edwin Smith Papyrus, which describes a case of breast cancer. We don't know the words for it because we don't have actually the vocabulary, but we can tell from the case description that this was a case of breast cancer. And certainly if you look at ancient specimens of cancer, cancer is present. This is a bone tumor found in a mummy from the ancient world, in which we know there's a physical presence of cancer in the ancient world. But there was no theory, really, that explained this for a long time. Cancer was thought to be a visitation of fate, a terrible a visitation of destiny, and left as such. Until, for the first time, the first theory of cancer began to arise. And that was promulgated by several physicians. We don't even know if there was one such physician or whether there was a conglomeration of them. But Galen, the great Roman physician, put forward the first theory of cancer, and that was that cancer was an excess of black bile. Galen argued that all diseases, all human physiology, could be explained by 4 major liquids that were fluids in the body: black bile, yellow bile, blood, and phlegm. I call it a hydraulic theory of pathology. One thing goes up, something goes down. And ultimately, he thought that all diseases would be explained by these 4, a kind of cardinal axis of a 4-dimensional axis. And in fact, there's only one other disease that Galen ascribed to an excess of black bile, and that was depression. In fact, the word melancholy literally translates to melancholy, black bile. And there's something very evocative about the idea that in the ancient world, right in the ancient world, the psychic and physical manifestations of a disease, depression, cancer, were linked together. It is not a coincidence that they still remain among the outer fronts of what can be treated by modern medicine. And very soon after this theory of black bile, there were attempts to surgically remove cancer, but also remove the bile from the body, as if to say that there's a systemic component to cancer, and that has to be bled out in this case. This is an archival picture of a so-called scaltatus mastectomy, in which the woman in this case was treated with surgery, followed by the bleeding of the removal, an attempted removal of black bile. But of course, unfortunately, as you can see from this very brutal procedure, many of these women would still relapse with breast cancer and die of breast cancer. But what was really missing was what I call the first revolution of cancer, and that is a very simple idea which blazed through the world somewhere in the 1860s and 1870s and was really consolidated by the early 1900s. And it's a simple idea, but a profound idea, and that is that cancer is a disease of cells. It is a disease of cells that don't know how to stop growing. In fact, at this point of time in the 1860s, there were very, very few diseases of cells, as it were. People ascribed lots and lots of different reasons to have diseases. Heart attacks were explained in particular ways. But cancer was now ascribed to disease of cells by a man. This is a much older picture of him. He was no older than 34 when he made this then a radical argument that, in fact, regardless of whatever the cancers were, breast cancer, melanoma, liver cancer, leukemia, most importantly, cancer of the white blood cells, were all tied together by one common pathophysiological mechanism, and that was an excess of cell division. These cells did not know how to stop growing. His name was Rudolf Virchow. He worked in Germany. In fact, there is something very chilling about being able to look through, as a cancer doctor, to be able to look through Rudolf Virchow's microscope, which you can do if you go to Berlin, you can. And in fact, Virchow made this very strong claim that cancer was a disease of cellular origin. Now, once again, very quickly, we moved from that understanding of cancer as a disease of cellular origin to the first attempts to now use that information and translate that information into cancer treatments. And the treatment which was made available contemporaneously with Virchow was surgery. So if it was a cell, a group of cells, a group of dividing cells, then we could cut the cells out and thereby cure cancer. This is a picture of Bill Roth operating in Austria. And in Bill Roth's clinic came the person who, as a student, the person who would really redefine and push the boundaries of the treatment of cancer based on the idea that cancer originated locally in an organ and could be therefore cured or removed by aggressive surgery, and that was William Stewart Halstead. Halstead was a young man when he went to Bill Roth's clinic, and in Bill Roth's clinic he learned to perform incredibly intricate operations. He came back to New York and subsequently went to Hopkins in Baltimore, where he started studying breast cancer. Now, in Bill Roth's clinic, Halstead discovered a new anesthetic called cocaine, and he was a very bold experimenter. He began to use it on himself to provide anesthesia because he thought he would use it in his surgery. And by the time he came back from Bill Roth's clinic, Halstead was a raging addict to cocaine. And he came from a wealthy family, and the drug of choice for cocaine addiction, to treat cocaine addiction, was another medicine then called morphine. And so this is not so Halstead was then treated with morphine to cure his cocaine addiction. But in fact, now he became dually addicted to both cocaine and morphine and remained so for the rest of his life. In fact, his closest surgical trainees, including his residents, would never know this. He would scrub out mid-surgery, apparently, inject himself, come back into surgery, and finish his operations. It was a testament to his self-discipline. The disease that Halstead thought that he would attack with his full ferocity was breast cancer. Halstead thought that he would understand the local treatment of breast cancer and push that with as much innovation as possible. And Halstead made a very bold conjecture, a very bold theory. He argued that if indeed cancer is a disease of cells, and if indeed cancer originates in a single nidus in the breast, then operating more aggressively and removing not only the tissue, but all its surrounding tissue should cure cancer. Now, and in order to prove this theory, in order to push this theory forward, he began to launch first a surgical operation called the mastectomy, and then subsequently a surgical operation called the radical mastectomy, in which the attempt was made to remove as much tissue as possible. And Halstead's students began to push this idea even more strongly, even deeply, and they began to move towards an ultra-radical or a super-radical mastectomy, all in the service of a theory that, of course, cutting more meant curing more. This is a picture from one of Halstead's original papers describing the procedure. The script at the bottom is from Halstead. It says, the patient was a young lady that I was very loath to disfigure because these operations were disfiguring. They were very, very difficult. They stretched into several hours, not only removing the breast, but the clavicle, tissues under the muscles under the breast, the pectoralis major, the pectoralis minor, and so forth, and also deep into the aorta, the nodes around the aorta, to try to cure cancer. Now, he was successful. Halstead was successful. In fact, many, many patients with advanced breast cancer would benefit from Halstead's very systematic dissection of the disease. The problem, as Halstead began to realize but never fully conceived, the problem, of course, was that for a woman in whom the breast cancer had already metastasized, a more radical surgery, a more radical operation would not help. It wouldn't, because, as it were, the cancer had already left its local confines. And ironically, for a woman who had tissue cancer was restricted to begin with, more aggressive radical surgery wouldn't help either, because you were doing too much for a cancer that was locally restricted. So in fact, peculiarly, it was perfectly mismatched to the two poles of cancer. Either for women who had local disease, doing more aggressive surgery was not helpful, or doing more aggressive surgery and disfiguring a woman who already had metastatic disease was not helpful. And it was this realization which took nearly 100 years, long after Halstead was dead. This realization took 100 years to really put into place. And it was only 100 years later that a clinical trial could be launched that ultimately tested the radical mastectomy against a simple mastectomy with radiation or a lumpectomy with radiation. And unfortunately, there was no difference. Now, you could ask yourself, why did it take 100 years? And there are several reasons behind it. Well, one reason is theories of cancer are very powerful. We want to believe theories. And experiments done in order to service those theories have to be performed all the time. We cannot become trapped by our own theories of cancer. No matter how powerful they seem to be, they have to be put into experimental, they have to be put to test experimentally. And in the particular case of the radical mastectomy, that experiment became very difficult to perform for several reasons. First of all, the word radical mastectomy. I mean, who would, if the word was radical mastectomy, who would subject themselves or their mother or their sister to the non-radical version of the surgery? The word itself became a trap in which surgeons would say, why would I offer the inferior version of therapy to a woman when I know that the word itself suggests that this is the most aggressive therapy for that particular cancer? And women, just to carry on that same legacy, women said, why would I give myself the inferior treatment? So in fact, this trial became impossible to run because no one wanted to enroll in the control arm of the trial. No one wanted to be, so, and people have described this. When you speak to surgeons from the 1950s and 1960s, they would describe this as water, water everywhere, but not a drop to drink. Patients, patients everywhere, but not one person to put on the control arm of the trial. And it took 100 years before. So this is, I think, in some ways, the first counter lesson to the idea of the theory of cancer. Theories of cancer are very important. We need them, but we also need to be able to disband them. Every theory needs to propose an experiment that will either prove or disprove it. And those experiments are carried out by patients. They're carried out by patients in collaboration with their physicians. Well, continuing this idea of theories of cancer, the local theory of cancer then moved on to the notion or to the idea that even if surgery was not sufficient, perhaps a more invisible knife, a different kind of strategy would now be successful. And in fact, around the time that Halstead was beginning to launch his radical operation, there arrived a piece of technology that would actually allow surgeons and their colleagues to intervene on cancer even without cutting into the tissue, and that was radiation therapy. This is a picture of Marie Curie, of course, the woman who found radium. This is actually an interesting picture. This is a child being treated at the Stanford Clinic, one of the first children. This is one of the first patient zeros being treated at the Stanford Clinic for an eye tumor, a retinoblastoma. We know a little bit about this child. Actually, he left a series. He was alive for about 70 years after this treatment, and he was cured through radiation treatment. And then a kind of darker note to all of this, which is that while on one hand, these treatments were successful, like surgery, in removing local cancers, they also began to reach a kind of fundamental limit. And that limit was that if you use these indiscriminately, they would actually not only cure cancer, of course, but they could also cause cancer. And that was a big mystery. It was a big, we'll come back to that mystery, because it did not fully explain how cancer could be a disease of cells, but why radiation put on those cells could cause cancer. Hold that thought, because we'll come back to it, because it's these disruptive thoughts, these things that don't fit, that ultimately generate new theories. So we'll come back to that idea in a second. But in fact, this is a picture of an advertisement that I found in a magazine from the 1920s of a paint called Undark. Undark was radium-infused paint, and someone thought it was a very good idea that you could paint your clocks with it, so that when you looked at your watch, you could wake up in the middle of the night and you could look at your watch. And in fact, young women were employed to put radium paint onto clocks. And many of them were encouraged, because they wanted to keep the writing sharp, they were encouraged to lick the brush as they went along. And in fact, nearly all of them were virtually glowing with radioactivity. Radium has an incredible ability to go into the bones. They became suffused with radioactivity, and almost all of them would die of complications of that radioactive induction. They would die of cancers. So it was in some ways a real-world demonstration of that dichotomy, that on one hand, of course, radiation could kill cancer cells, but for some reason that really didn't make sense, a mystery, that it would actually also cause cancer cells. So there was something missing in the cellular theory of cancer, which needed to be revisited, as it were, and we'll come back to that thought. And in the middle of all of this, while surgery and radiation were trying to cure cancer locally, the thinking grew and urgency grew that perhaps we needed something more than just surgery and radiation. We needed a third modality, and that was chemicals. Chemotherapy, of course, literally means chemical therapy. The word chemotherapy was first applied not to chemotherapy as we understand it, but to antibiotics, because they were chemical therapies in that case for bacterial diseases. Paul Ehrlich was the first person to invent some of the first antibiotics. And Paul Ehrlich spent the last part of his life looking for not just antibiotics, not just things that would kill microbial organisms, but actually kill cancer cells and discriminate killing cancer cells from normal cells. So Ehrlich argued that surgery and radiation were good enough. They were important modalities for the treatment of cancer, but we needed a third part of the triad. And that third part of the triad was chemicals. These chemicals would go into the body. He thought of them as microscopic surgeons who would go into the body, excise cancer cells, kill them, sparing normal cells, and thereby, and he was actually the first person to invent a lovely phrase for them. He called them magic bullets. It's a word that rings through the history of cancer chemotherapy for its history. And they were magical because they would discriminate between the cancer cell and the normal cell. Paul Ehrlich died, little realizing that, in fact, the very first chemical treatments for cancer would be not magical, but at least bullets, because they came from war gases. So in the mid 1900s, for the first time, as you know, as the war broke out, new gases were invented, toxic gases, poisonous gases were invented. And this is a picture of mustard gas bombing in Italy, in Bari Harbor. And very soon, pathologists, including a pair of pathologists from this university, from Stanford, noted that in soldiers who had been bombed with mustard gas, there was a rapid depletion of white blood cells in their bone marrow. If you looked at their bone marrow, the white blood cells had disappeared. And so these pathologists made the conjecture that if this was really true, and if all the other tissues were left behind, maybe if you took a different concentration of this mustard gas and you gave that mustard gas intravenously, maybe you would kill white blood cells that had turned cancerous and spare the rest of the body. It was a bold conjecture, and in fact, it was tested very soon after in the 1950s at Yale, at Memorial, at Columbia, and it was found for the first time that if you diluted the mustard gas and gave it appropriately, you could actually give patients you would give patients remissions from cancers. The very first cancer to be thus treated was a silversmith was given, he was about 50-odd years old, was given a diluted version of mustard gas with a big lymphoma. He had a remission, but unfortunately would relapse and die later. But this idea that you could now take a chemical poison, a poisonous chemical, really an inhibitor of cellular growth, something that kills cellular growth, and if you gave it under the right circumstances, that you could somewhat selectively kill cancer cells and spare normal cells, is the basis of of much of modern chemotherapy. It is the basis of nearly all of chemotherapy that predated the 1980s, but it is the basis still of much of modern chemotherapy. We'll come back to this idea again in a second. But that was all because of the discovery of these mustard gas bombings and their consequence. Now, there are several features to be noted about this idea. Number one is all these drugs were discovered empirically. That is, that they were found essentially by accident, in the case of mustard gas, by accident. And they were discovered as general inhibitors or chemicals that would, in general, dampen cellular growth. So it was based, again, on a simple single theory. We're still talking about a theory of cancer which had arisen in the 1900s. We're now in the 1950s, but the treatments of cancer still are going back to that simple statement: cancer is a disease of cells. It is a disease of growing cells. And in fact, more and more such chemotherapies were deployed, and by the mid-1950s, there was not one, but two or three of them, empirically discovered cellular poisons that killed growing cells and appeared to have a narrow selectivity for cancer cells versus normal cells, all dependent on that simple statement, on that simple hypothesis about the cellular origin of cancer. And the next series of drugs came out of Boston, and those were antivitamins, so not killers of cellular growth derived from mustard gases, but also accidentally discovered, serendipitously discovered antivitamins that would kill bone marrow cancers in this case. And that was work done by Sidney Farber, who was a pathologist working on children. Now, Sidney Farber particularly focused on a disease called children's acute lymphoblastic leukemia, a variant of leukemia which was very lethal in children. And he began to use antivitamins for that same purpose. But essentially, we're still talking about, as I said before, empirically discovered chemicals which happen to be inhibitors of cellular growth, going back to Virchow's hypothesis about cancer as a cellular disease. On just a quick side note, a little story here about I became very interested in the very first patients who received chemotherapy. I think of them as kind of our first teachers, the patients who really mark the important moments in this journey. And I knew, for instance, that if you look at a scientific paper, of course you can know what the patient, you know something about the patients, but their names are anonymized. One of the interesting things about writing medical history is that you have to remove that. You have to go back behind the paper, as it were, move the curtains back, and find who the people were. You have to make them into human beings again. And so I was interested in who these first patients were, and I knew that the first child to be treated with chemotherapy was a child whose name was RS, but I didn't know anything more about that child. So I was in Boston, actually sitting in Children's Hospital where Farber had been working, and I went on a quest to find RS. And I started writing emails. I became somewhat obsessed with it. I wrote 100 emails trying to find this child, and nothing came back. This was in 2006. I was buried in the middle of my book. And then I thought, I became really dejected, and I went to India, to my parents' house for a vacation. And someone said, there's a historian of chemicals who lives 3 blocks from your parents' house. Now, we're 6,000 miles away from Boston. And said, go visit this guy. And I went. It was in the evening. I said, well, I have nothing else to do. So I walked over a few blocks from my parents. I had a long conversation with him. And then I was leaving. It's a kind of midwinter evening, and he says to me, by the way, I was in Sidney Farber's clinic in 1971. I said, really? And he said, and he gave me a roster and pictures of several of his patients, including all the first people who were on trial. Would you like this? And he plucked it out of his shelf, and he handed me this. And this, of course, is a picture, which is not on any searchable index. It is actually from a magazine, an evening magazine, from Boston of 2 children, and his name was Robert Sandler. RS was Robert Sandler. This is how you write books. You have to travel 6,000 miles away, find something, and then come back. So interestingly, I could come back then exactly to the same desk where I was working, and now 10 minutes away from there was this child's house. I could actually go to the house, and in fact, the Ken Burns film begins at the house. It begins at the child's house. And so I dedicated my book to Robert Sandler. My book is dedicated to Robert Sandler and those who came before and after him, as a kind of homage to everyone who serviced us by providing the kind of knowledge that we need to move cancer forward. Now, this story, which is a circular story, going far away to find something that is next to you, has a kind of second circle of stories, which is that about a few weeks after my book was published, I got a phone call in my office from this gentleman, and that's Robert Sandler's twin. So to imagine the dissociative experience. So his name is Elliot. Imagine the following experience. You go, he lives in Maine. You go to a bookstore. I hadn't heard of him. He hadn't heard of me. You go to a bookstore, and you're interested in cancer because your twin died of it as a child, this child. And you open a book and you find it dedicated to your brother, which is what happened. So he of course found the book, and then he called me up, and so I got to know, of course, the full story behind all of this. I'm going to tell you one more story, which is important. The mother here is Helen Sandler. I had the opportunity to meet her, and Helen Sandler said to me something very, thankfully, fortunately, my book won lots of awards. But to me, the most important comment that anyone has ever made about Emperor is Helen Sandler's comment. She said to me, when Robert died, Sidney Farber begged her to perform an autopsy on the child. And she said, no, he's had enough. He's gone through the terrifying treatment. I just want his sanctity maintained. And he kept insisting. He said, this is the only way we will learn. Do it not for me, but for children who will come afterwards. And finally, she relented. And she regretted that decision her entire life. And she said to me that reading my book, reading about Robert again, sort of closed that circle. So 3 full circles, as it were, of journeys that came around fully. But a reminder, again, of what the role that people like you, patients, people like me, physicians, and the role that we have together in moving this vision forward. That idea that now you had not one chemical, but now several chemicals, all, as I said, empirically discovered chemicals that stopped cellular growth, was brought to its full fruition by studies that followed this in the 1950s and 1960s. This is a picture of 2 men, then very young men, who moved to the National Cancer Institute in the 1950s, who began now to take one such chemical and combine it with other chemicals. So this is the birth of what we recognize as combination chemotherapy, 2 or 3 chemicals now of inhibitors of cellular growth or cellular metabolic poisons that allowed them to now deploy these in combination against cancers. And they, much like Sidney Farber, focused on blood cancers, and in particular on the same disease that Farber had become interested in, which was acute lymphoblastic leukemia. And others, this is a picture actually taken, again, not very far from here, probably a few 100 feet from here, of another giant in this field, Henry Kaplan, who began at Stanford in the 1960s to not only combine chemotherapies, but also combine chemotherapies with very carefully directed radiation to try to see if you could cure another disease that was at that time very difficult to cure, and that was Hodgkin's disease, Hodgkin's lymphoma. And together, these efforts by the mid-1960s revealed a very important series of results. Number one, it was found that for certain cancers, Hodgkin's disease and for lymphoblastic leukemia, in fact, the combination of these chemotherapies could achieve cures that were previously unachievable. So just to give you an example of that, acute lymphoblastic leukemia, when Robert Sandler walked into Sidney Farber's clinic, had a mortality rate of 100% and a cure rate of 0%. By the 1950s, because of the efforts of Emil Frey and Freireich, and some of the efforts of Henry Kaplan in that disease, that cure rate had climbed to 40%. By the 1960s, it had climbed to 70%. And by the 1980s and 1990s, the number that we have right now is around 80 to 90%. So this disease was completely incurable in 1950. In the span of 25 years, became largely curable, although there are still struggles in that disease itself, but became largely curable. So a transformative effect in that disease. Hodgkin's disease, metastatic Hodgkin's disease, had a cure rate of 0% in the 1940s and 1950s. By the 1960s, because of the efforts of Henry Kaplan and his many colleagues, had climbed to around 40, 50, and 60%, depending on the subtypes that you had of Hodgkin's disease. So real strides in some diseases. But what was also clear from these original trials by the 1970s, that there was also a failing, that somehow or the other cancers, metastatic breast cancer, metastatic pancreatic cancer, colon cancer, prostate cancer, were not so easy to cure with these combination chemotherapies. In fact, the toxicities often overwhelmed the cure rates that were being achieved by these combination chemotherapies. So something was still missing. There was a missing element. And we had to now, I said this before, the Red Queen had now to move again and start building up a different strategy to move forward, because the world of cancer had all of a sudden began to move faster in the opposite direction. A new, ingenious strategy was needed to move forward. Some of that strategy came not from cancer physicians, but in fact from cancer advocates working in the community. There's a picture of Mary Lasker, whose role in this history is enormous, not because she was a cancer researcher, but because she really dedicated herself to cancer researchers to be able to move their activities forward by what she called not fundraising only, but friend-raising. She was probably the most fierce advocate of biomedical research, still remains one of the most fierce advocates of biomedical research. Even after her death, her foundation continues to be one of the most fierce advocates of biomedical research. And she began to campaign everyone that she knew, nationally and internationally, Congress and many others, to really focus on cancer and launch what would be called the war on cancer. So much so that if you woke up in 1969, you would find a newspaper advertisement, a full-size, full-page newspaper advertisement, which said, "Mr. Nixon, you can cure cancer," with cancer cells eating up the bottom of that last word. And the idea was that, launched by Mary Lasker, the idea was, look, we've had astonishing successes with a few cancers: Hodgkin's disease, lymphoblastic leukemia, certain variants of breast cancer. Why don't we now just consolidate these successes and pour national resources in a focused way to build the so-called war on cancer? And this is really the announcement of the war on cancer, the National Cancer Institute Act, which became the war on cancer. And indeed, the astonishing advancements, all based, of course, going back to that simple idea, the astonishing advancements indeed did raise a huge public interest in transforming the world of cancer, and the war on cancer was announced, as you very well know, in 1971. And then reality began to hit, and this is the reality over here. So this is the announcement of the war on cancer, the expansion of the National Cancer Institute budget as resources began to be poured in to the war on cancer. And on the right side, now tracking down from the 1970s to the 1980s, in men and women, the actual mortality rate from cancer. The red line is the expected rate if things had moved on, the actual mortality rate, which was expected in the 1970s to look like this, but in fact looked like this. And that was the sobering realization that something was still missing, that in cancer prevention and in cancer treatment, that we hadn't innovated enough to be able to change this line, as it were, from a plateau into a deeply dipping curve. And so all of a sudden, it was as if the war on cancer had presented not a challenge to cancer physicians, but a challenge to all of us, cancer physicians, cancer activists, cancer advocates, people with cancer in their families, to now rethink, go back to the drawing board and rethink, and now come up with a second line or second strategy of trying to figure out the attack. Well, the only way we know forward is through reason. The activity of reason is the only mechanism that we can deploy to move forward in any disease, and in particular in cancer. So going back to the drawing board meant going back to a theory again, which brings me to the second idea, as it were, of cancer, the second phase of cancer research, the second idea of cancer biology, and that is that cancer is a disease not only of cells, but of genes. Now, remember, way back when, remember that peculiarity, that sand in the eye of cancer theory, which was radiation, for some reason, was able to not only cure cancers, but cause cancers. And several people over the intervening 30 or 40 years had wondered, why is it that radiation, they must be doing something to the cell that causes, or changing the cell in some way that causes cancer. And in the meantime, several people had figured out that one thing that radiation does is it changes genes. It causes mutations in genes. And it was through that line of thinking, as I said, a sand in the eye of cancer theory as a disease of cells, that began to illuminate the idea that, in fact, cancer was, of course, a disease of cells, but in fact, what was really changing were genes. And so there are several actors in this, several players from here, from around the world. I won't name all of them, but the essence of the theory was the following. That is, that the very genes that cause normal cellular growth, if you mutate them, if you change them, for instance, by virtue of X-rays, you release malignant cellular growth, and ultimately that's cancer. Now, we take this idea, many of us take this idea for granted now, but this was an extremely radical idea in the 1970s and 1980s. Many of you who actually remember the first times this idea was announced, it of course was a revolutionary idea and also a very chilling idea, because here we were hoping that in fact it was going to be easy at the genetic level to dissociate cancer from normalcy. But what the genetics told us was just the opposite. The genetics was telling us was in fact that the very genes that control normal cellular growth, that allow your embryos to grow, that allow our hands to grow, that allow wounds to be healed, that allow stem cells to grow, if you mutate those genes, you ultimately release abnormal growth, abnormal cellular growth, and that causes cancer. Now, the important consequence of this is that cancer therefore becomes a disease really like nothing else. It becomes a disease in which normalcy and illness are twinned, like Robert and Elliot Sandler. They're part of the same spectrum, and that small changes from normalcy, the very genes that control growth, now become manifest in their malignant form in cancer. And this began to explain, of course, why cancers were caused by environmental influences. This is a picture of Percival Pott, who actually one of the first people to figure it out. This is the Surgeon General announcing that, in fact, tobacco causes cancer. If you didn't have a genetic theory of cancer, it'd be hard to explain how things like chemicals in the environment would somehow or the other coax your cells to start dividing abnormally. If you had a genetic theory of cancer, you could now say, well, the real missing link is it's genes plus environment. The environment impinges on genes, changes their structure, it causes mutations, and thereby releases cancer or causes cancer. And that led to the third idea, or the third phase of cancer, the third general phase of cancer biology, cancer theory, cancer treatment, and that is cancer is a disease not only of cells, not only of genes, but as it is of genomes. By genomes, of course, we mean not one gene, but the entire complement of about 20,000 odd genes that all human beings possess. So every cell has a complement of about 20 to 25,000 genes, and cancer is a disease where not one gene is changed, but multiple genes have to be changed. So going back to trace this intellectual history, we understood that alterations in growth causing genes cause cancer. The question is how many, how common are they, what are they, what is their identity? And in fact, several studies indicated that in fact not one gene was insufficient, that you'd have to have many genes, that in fact our cells had natural barriers against growth. Growth is a very, very fundamentally important process for us, so important that our cells have complicated systems to compute whether they should grow or not grow. A decision for a cell to grow is an incredibly important decision, and it requires more than one decision point. And it's when many such decision points are abnormally altered by mutations in genes that you ultimately release a cell that can't stop growing or grows abnormally, and that, of course, is cancer. So I want to spend a few minutes here because now we're beginning to come close to how cancer biologists understand cancer. So we're now beginning to circle a very contemporary description of cancer from the scientific point, but it has many, many important implications about how we go ahead and what happens next. So here is a hypothetical picture of a woman who comes into a clinic. Let's say she has breast cancer, and the blank sheet of paper, forget about the dots for a second, the blank sheet of paper has every gene in her body, all the 24,000 genes in her body. And the first gene is on the top, and you have every gene sort of printed out all the way to the last one. And you have the capacity, which we do now, because of technology invented here and other places, we do now have the capacity to ask the question, what genes have changed in her breast cancer cell? What are the alterations of genes? So obviously some genes will be genes that are involved in regulating or computing growth control. And you find that you have 1, 2, 3, 4, 5, 6, 7, 8 genes that have been altered in this woman, and they're spread out in this kind of landscape view. Now here's the important point, which is that the next woman comes in, also with breast cancer. If Virchow were to look down his microscope 100 years ago, he would say, well, both of these are breast cancer. They look identical under the microscope. There's no difference about them. And yet when you look at the genetic anatomy, the genomic anatomy, you find that there are some shared genes that are changed in 2 breast cancers, but there are some unique genes as well. So every breast cancer is its own breast cancer. And then a third person comes in, a third woman comes in, and here too, you see some commonalities, but here is another breast cancer, which is its own breast cancer. Now you begin to now understand the kind of complexity that cancer biologists are dealing with. They're dealing with a disease whose, number one, genetic anatomy begs the difference between normal genetic anatomy because the genes that control growth are very closely allied to normal genes that control growth. And number two, they're dealing with diversity of a phenomenal level. In other words, every individual specimen of an individual kind of cancer is its own cancer. And that is, of course, the challenge for us. That is the challenge. You can create these things called maps. You can take genes that are common and make them into big peaks, and genes that are uncommon and make them into small peaks. You can condense this information using complex data algorithms into a picture. And this is actually, now you're staring the enemy in the face. This is what the human cancer genome begins to look like. This is from colorectal cancer. This is work done by Bert Vogelstein. And what you see here are big peaks, denoting the very commonly altered genes, medium-sized peaks denoting less commonly altered genes across many specimens, and then, of course, these dots. This dot, for instance, refers to one gene which is unique to one specimen of colorectal cancer, not present in any other specimen of colorectal cancer. So the job now, therefore, is to annotate every single one of these genes and ask the question, is it driving the cancer? Is it not driving the cancer? Is it incidental, not incidental? Can there be a medicine directed against this variant, and can there not be a medicine against that variant? Now, you could say, oh my God, that job is impossible. This is an impossible. The diversity of cancer on one hand, and also the fact that normal growth and abnormal growth really depend on the same genetic complement, those two tasks make it impossible. But if that was the case, of course, we'd have given up long ago. We cannot give up. So we have to keep now looking gene by gene and piece of anatomy by piece of anatomy to try to, genetic anatomy, to try to move forward in trying to treat cancers. And in fact, it's not all hopeless because, in fact, you can do that. Way back, even in the 1980s, when the first genetic maps were being figured out of cancer, there were already attempts. This is a picture of an important trial from China and France, which allowed the targeting of a particular variant of leukemia, acute promyelocytic leukemia, APML, with a single medicine. And just to tell you, if you find these medicines, the effects can be dramatic. Acute promyelocytic leukemia was the most lethal form of myelogenous leukemia ever. So in other words, if you had the unfortunate luck of having myelogenous leukemia, not children's ALL, it's a different disease, myelogenous leukemia, if you had that disease, you would say to yourself, thank God it's not acute promyelocytic leukemia, because that is a virtually uniformly lethal disease. And yet the introduction of one medicine, retinoic acid, changed that disease to the one leukemia that you would want to have if your cup were to run it over in that direction, because it is now the most curable variant of acute myelogenous leukemia. So it's like flipping a switch. You literally flipped a switch, and all of a sudden a disease that was incredibly lethal, with the appropriate genetic annotation, the appropriate research, the appropriate trials, began to be a much more curable disease. Still not fully curable, but much more curable disease. And this experience has actually been repeated gene by gene, example by example in other cancers. And yet there remain big challenges. This is a picture of chronic myelogenous leukemia, yet another disease, doesn't resemble the other leukemias. Brian Drucker, who found, along with working with a team of other chemists and scientists, who found that, in fact, you could take a molecule and you could lodge that molecule like an arrow into the gene that was driving this particular cancer, one of the most, again, a cancer that was very, very lethal. And then all of a sudden, you could convert that cancer into a chronic disease for most patients. So much so that patients who are responding to Gleevec really don't have a lifespan that seems to be any different than patients who don't have leukemia at all. Their lifespan is normalized. They still have to take a pill to keep the remission going, but it's a really remarkable development in that cancer. And this has been repeated elsewhere with other cancers that may be more familiar to you. This is breast cancer, HER2-positive breast cancer. Again, a careful analysis of its genetic anatomy, finding one common gene that seemed to be present in multiple specimens of HER2-positive breast cancer, and this is patient 0 of HER2. She was the woman, Barbara Bradfield was a woman treated 16 years ago with an antibody, in this case, for this cancer. She had metastatic breast cancer and actually still survives today with a breast cancer that was virtually untreatable about 16 or 17 years ago. And this particular variant of cancer just last month had 3 more medicines that came out for this particular variant of breast cancer. So again, a series of remarkable treatments for selected cancers as we move forward with this anatomy, genetic anatomy. But then, like all theories, even this begins to come to its peak. And it's a reminder why we need to keep moving forward, keep moving, innovating. This is a picture of CML, chronic myelogenous leukemia, now treated with that new drug I talked about, now no longer new, called imatinib, Gleevec. And you see the patients who didn't receive the drug dropping off in survival in contrast to patients who did receive Gleevec. So as I said, a large change in survival. And this axis is on the order of 70-odd months. So this is a significant amount of time, 5, 7, 10 years of remission and some treatments as well. This is breast cancer treated with Herceptin, another targeted therapy, genetically annotated targeted therapy for breast cancer. And now what we see is that the metastatic breast cancer, you see that the months have shrunk. We're now at 50 months over here with a patient with metastatic breast cancer. Still, patients who receive drug get an enormous benefit, but it's not like Gleevec. The cancer is more complex. Its genetics is more complex. The therapy is more complex. And the gains still present are now more modest compared to compared to Gleevec. This is melanoma, again, a cancer that we've begun to understand. We have begun to understand its genetic anatomy. And now we're shrinking down to this metastatic melanoma, shrunk down to about 10 months. Still patients with a little bit of benefit, but at the end of those 10 months, with a targeted therapy against their melanoma, against the genes that are driving the melanoma, but the cancers develop resistance, and then the patients die as a consequence of the resistant disease. So it is now, we are living, right now, this moment, we're living through the end of one other era of cancer therapy, which is genetically directed cancer therapy as a single agent. We're finding out that in truly complex cancers, even that won't do. We need to innovate once more again. We have to go back to the board and start afresh to try to refresh what happens next. So I'm going to spend the last few minutes talking about my visions, and actually my visions that are shared by many people in the cancer field about what happens next. What do we do from here? Where does the drawing board go back? To me, what's interesting, what's exciting, is the capacity to now incorporate all these pieces of information in a way that's data-driven and then convert that into new treatments, prevention, and potentially cures for some cancer. And it's based on an idea which is now taking root, and that is that cancer is not just a disease of cells and genes and genomes, but it's an organismal disease. It lives in organisms. It lives in real human beings, and it's sustained by physiology that lives inside real human beings. So by organismal, I mean we think of organisms as having physiology. They have environments, they have interactions. So can we now think of cancer having physiology as well? What does the physiology of cancer look like? And if we can take now not just the genetics, not just the cellular biology, but if you can think about cancer as a physiological entity, can you now intervene on cancer physiology? Organisms live by virtue of complex pathways. They live within complex networks. Well, we need new data and ways to integrate big data into a way that makes sense of the physiological networks that sustain cancer. So just to give you one example of this and how data plays into all of this, I mean, if you ask someone in the 1980s how cancer occurred, this is the time of the genetic theory of cancer, they say, well, there's a mutation, it changes a gene that causes cancer. You came back by the 1990s, now all of a sudden the mutation sits at the top of this, and now you see a network of connected events that allows the cell to be dysregulated, grow abnormally in a physiological sense, and that ultimately causes cancer. And this is now the same pathway in 2014. That's what it looks like now. So you see individual nodes communicating with individual nodes, and you say, my goodness, this gives you a headache. But to biologists, it doesn't give us a headache, actually. This is because we need to know, instead of building simplified models, we need to understand what the level of complexity is, because then we can go back and try to intervene on single networks. So it's not one gene mutated and all of a sudden, boom, you get an abnormality in growth control. It is that the alterations in genomes are causing alterations in cellular physiology, the way cells digest chemicals, the way cells eat sugar, the way cells consume oxygen, the way they interact with the immune system. All of this is happening, and ultimately that is what is unleashing the abnormal growth of cancer cells. And this is true not only at the microscopic level, but it's true at the macroscopic level. I'm going to end with this last study, which emphasizes that this understanding of cancer in a physiological sense extends not only to organisms, but to networks of organisms, to societies. This is a study which I find fascinating, which was performed in Framingham, in Massachusetts, in which I actually went to the study site, in which they asked the simple question, which is that we know that smoking is a major cause of lung cancer, lip cancer, and other kinds of esophageal cancer, et cetera. And we know we've spent decades trying to figure out how to stop smoking. There are taxes, there are campaigns against smoking, you watch the television, and yet smoking persists in a kind of metaphorical analogy in the same way that cancer seems to persist in human society. So can we get rid of behaviors that cause and sustain cancers in society? So what they did was very interesting. They went to this village, a small town in Massachusetts, and they said, okay, we'll create a social map of every interaction with every other individual. So in other words, if you played golf with Mr. Jones, you'd be connected in this map. If your neighbor is another person, that's another connection. Your uncle is this connection. It's Facebook but before Facebook. So they created a social map in this manner. And then they asked a very important question, which is that now, on top of that social map, the social network, I'm going to now superpose smoking behavior. So every dot here in 1971 corresponds to whether you smoked or not, how much you smoked, et cetera. And then they asked the third question, which is now I'm going to follow this network over time. So I'm going to move this network from 1971 to 2000 to ask the question, who continues to smoke despite the anti-smoking campaigns, who quits and who starts? And what's very interesting is that in the end, the people who continue to smoke versus those who quit, really one of the strongest determinants are their neighbors, their social neighbors. In other words, the social network is an independent determinant. The social physiology is an independent determinant of whether you quit or whether you stay smoking. And so it really begins to make us rethink about addictive behaviors or behaviors in general that are cancer-causing or not cancer-causing. Taxation won't help that necessarily. What you need is you need to understand what the structure is, what the physiology is, in this case, a macroscopic physiology, and now rethink how can we, excuse me, infiltrate those networks and disable them in the same way at a microscopic level how you can infiltrate and disable individual cellular networks that cause or sustain cancer. So we've gone on a big journey, and I'm going to stop here. The journey begins with cells, it moves to genes, it moves to genomes, and ultimately ends in physiology. And it's something very satisfying, I think, in being able to come back to this idea over and over again and emphasizing that we need innovation at every stage. And the minute we stop innovating, the world will switch and throw us behind it. Thank you very much. Thank you.
Well, please join me again in thanking Dr. Mukherjee for an incredible talk.
Thank you.
I'd now like to open the floor for a few questions, just by brief introduction. My name is Amir Dan Rubin. I'm the president and CEO here at Stanford Hospital and Clinics. And probably like all of you, I am just super excited about this great journey that you have taken us through, but even more excited maybe about the future. So let's open it to the group. There are microphones in the middle, and we have our orange shirt people handing out microphones. And yes, ma'am, we have our first question over here.
Yes, I have a question. I am currently a multiple myeloma patient, having gone through a stem cell transplant. I'm soon going to be 69, but my first attack where I was told I had cancer, I was 20, and told I had a brain cancer. I did not, but I underwent all kinds of nasty treatments, and then went on to 5 bladder cancers, and then on to breast cancer, and then on to an ovarian cancer. And when people ask me what was my cancer of origin, I honestly believe it was changing my blood chemistry with some of the treatments that I had underwent when they thought I had brain cancer, which included mercury brain scanning tests and a bunch of other things that came about as a virtue of the fact that there were no MRI, CT scans, or whatever else back then. Is that a valid idea possibly, or no? I mean, I don't know what my cancer of origin is, but I really think since all the way since 1976, I've had anemia and severe blood cancer problems. I honestly believe that I probably had multiple myeloma smoldering along all along.
Well, I
And-
think it's certainly, I don't know what exactly you were treated with, but we know that some of the cancer curing reagents are carcinogenic in themselves. I mean, this is an unfortunate bargain that we had to take and have to take still, actually. Still, we're in an era where we have to take a bargain between cancer treatments. It is my hope that we won't have to do this anymore. In other words, it's my hope that in 10 years, we will really be able to laugh at our previous attempts, fumbling attempts at chemotherapy. And I really, really sincerely hope that we will be able to, by the beginning of the next decade, begin to bring therapies which are much, much more targeted towards individual alterations in genes. In particular cases when there are multiple cancers in families, it's actually worthwhile asking the question whether there's a genetic component to this as well. Almost always, there's an interaction between genes and the environment. Just to tell you what the unexplored quality of that is, I'll just give you one example. If you take breast cancer, and you take familial breast cancer, in which we know that there's a family history of breast cancer, and that's why it's being caused through multiple generations. When you ask the question, how many of familial breast cancers can be explained by the genes that we know already cause breast cancer, the answer is about 30%. So in other words, 70% of cancer, where we know that there's a family history, and there has to be a genetic component, at least a genetic component, 70% of those cases, we still don't know what the actual genes are. So it is really and the only way we'll know those genes is if those patients collaborate with physicians, if we form alliances and figure out how we could, because this is technologically now available. This is technologically possible. So, if I had to make a conjecture, I would say that it was probably a consequence of chemotherapies, but it sounds like there's some genetics that needs to be explored, and maybe we are at the stage we could probably explore that.
When do you declare cancer as cured? I mean, person has cancer, you give him one of these magic treatments, and 5 years later it pops up again, and maybe he dies of a heart attack. So, is the cancer cured?
Well,
in
so
your
there
studies?
are some. So the answer is it actually depends on the kind of cancer. One of the things that I think has been a learning experience for the medical community as well as for patients is that that the pace of the original cancer dictates when a person is declared cured or not. And number two, that in fact now we can go back with much, much deeper technology and understand whether the new relapse of cancer is because of a second cancer that arose or because it was that original cancer now coming back and relapsing after prolonged remission. We actually still don't know for many, many cases. Now, for rapidly growing cancers like leukemia, usually that number is 3 to 5 years, because if by 3 to 5 years, usually those cancers have stopped growing. But they're slow-growing tumors. Just to give you one example, metastatic breast cancer can be in remission for 15 years and relapse. Metastatic colon cancer can be in remission for 12, 13, 14, 15 years and then relapse. In contrast, usually leukemias don't behave like that. So it really depends on the kind of cancer. But 10 years ago, we had very, very few tools which would allow us to answer the simple question, which is the second cancer new, or is the second cancer a consequence of the first cancer? Those tools are clearly present now. We have those tools without a problem. So looking forward into the future, that is a very important distinction. If it's the same cancer coming back, then of course treating you with the same therapies is not going to help. If it's a different cancer, then we can actually treat you with the same therapies, particularly if they were effective the first time around. And this technology has already been covered. We have this technology. It will become available. It's already become available for leukemias. So it's an important technological innovation already available.
Today versus 50 years ago or 20 years ago? And secondly, I guess what's really behind my question is, are there things in our environment today, I'm making the assumption that there is an increase in cancer rates here, maybe incorrectly, but are there things in our environment, or in that we all carry cell phones, or there's a lot more chemicals in the food we eat? Are there things that maybe contributing to that?
Yeah. So two very important questions. So let's talk about the increase in cancer rates. So it is a very, you might think that it's an easy to answer question, but it's an incredibly difficult to answer question for the simple reason. I'll give you a couple of important points about it. Number one is, if you begin to look, you will begin to detect earlier and earlier cancer because technology keeps evolving. So of course, if you looked naively, or if you looked at a quick glance and asked the question, well, what happened to breast cancer rates? Well, you look like this. And the reason it looks like that is because if you point to that kink in the curve, that's when mammography is introduced, right? So it'll look like this because you've introduced a technique to diagnose cancer earlier and earlier. And once you have that technique, of course, earlier and earlier cancer will be diagnosed. So you will be falsely assuming that you, in fact, have an increase in the rate of cancer, in the prevalence of cancer, when it actually doesn't actually change. So you have to be careful about that piece. What you can do, so really the metric that works very well is a very difficult metric. I'm going to talk about it. I talk about this extensively in the book. And that is that cancer-related mortality is immune to all of these changes. In other words, the question that we should be asking is, are more people dying of cancer today than they were dying of cancer 10 years ago or 15 years ago? That's the question to ask. Now, that question is also a complicated question because, of course, the whole population is aging in general. So the population is expanding over time. And so if you look at that, of course, there'll be more cancer-related deaths in 2014 than there were in 1984 because the entire cohort of population has expanded. So what we do in order to correct for that, there's a way to correct for that. So you use a very careful statistical trick, I describe it in the book, to correct for all of that. So you can now really compare apples to apples, 1988 to 2010. Now, if you do all of this and ask the question, with the appropriate controls, is cancer-related death changing? The answer is complicated, but important. I have a slide, and I'll show you what the actual cancers look like. So let's talk about real data rather than talking in the abstract. I didn't show the slide because I was anticipating the question. So this is what it looks like. So on this side, this is cancer-related mortality, so immunized against early diagnosis. And what you see is a huge variation between individual forms of cancer. So just to give you some examples, some highlights of this. This is lung cancer. And this is explicable. So this is because of smoking. So essentially, this peak, this rise, is a consequence of smoking in the 1950s, 1960s, first among men, then following among women. If you were to divide this curve up into men and women, you'd see that. And this fall is because of tobacco prevention. This curve goes out, I think, into the 2005 or something range. This curve has continued to fall. Here's leukemia. We talked about leukemia. You can see a slow decline over time. And that is because of treatment. It has nothing to do with prevention. You can't really prevent leukemia at this stage. We don't know how to prevent leukemia. But that's because of treatment. Lymphoma, similarly, because of treatment. Colon cancer because of treatment. Cervical cancer because of prevention. So because of pap smears, and now to some extent because of vaccines. If you were to look at pancreatic cancer, it looks like a flat line right through. If you look at prostate cancer, it goes up a little bit and then comes down again. So in each individual form of cancer, these are the individual trends. Now, if you now were to slap everything together, what would it look like? It looks like a line that starts off, it grows, really driven by lung cancer. It grows over the 1970s and 1980s, grows to its peak in the 1980s, begins to plateau. This is now aggregate. I'm talking about aggregate in general. And has begun to plateau and has begun to drop down by about 1% to 2% every year. So that is the aggregate. So I'm sorry that's a long answer, but we have to talk about very real numbers here. And it is cancer dependent. It has to be mortality. It can't be cancer prevalence. For many cancers, the cancer mortality has decreased. For many cancers, it's remained the same. And for some cancers, the changes have been dramatic. Now you can take that and put it in your hat and smoke it.
All right, we have time for one more question. One more question, please.
I have a question here. Can you hear me?
Yes.
Is it on? They tell me that lung cancer leads to brain cancer. Now, is that so?
No, it doesn't. So often when they're saying what they really mean is that there are certain variants of lung cancer that metastasize or can metastasize to your brain, and then they're called brain cancer, but in fact not brain cancer at all. What they are is lung cancer that's moved to the brain.
Okay.
And it should be treated as, so one of the things that we found out, we know more and more, is that when lung cancer goes to the brain, for instance, or when breast cancer goes to the liver, it doesn't become the liver. It remains breast cancer in the liver. In fact, one of the challenges to figure out how to treat breast cancer in the liver and what the similarities and differences are between one and the other.
Yeah, that was the question. But the other question was, if someone has prostate cancer and then has a melanoma and then has leukemia, no, not leukemia, lymphoma, is that related to the
So again, it would go back
cancer?
to the question that this lady was asking. And so to take a step back, there are two major influences over here, right? So one influence is the environment. The second influence is genes. And we know cancer is a consequence of the intersection between those two. Genes are activated or inactivated by the environment, ultimately leading to cancer. So whenever I see a patient like this, I have always asked this very simple question. What are the environmental influences? What are the genetic influences? What are the influences from the family history? And are these random, right? So if you now compute all of these together, 10 years ago, we had absolutely very little technology that would allow us to discriminate all these pieces. These pieces seemed as if they were sort of different parts of the chessboard. Now the technology exists to put these four things together and ask the question in a much more intelligent way. The problem, and here's the problem. The problem is, even today, if such a case was to arise, we would treat that patient with lymphoma therapy for lymphoma, leukemia therapy for leukemia, myeloma therapy for myeloma, brain cancer therapy for brain cancer. It's as if, you're touching the elephant and you have, some person sees the tail and treats the tail, some person touches the trunk and treats the trunk. You have to integrate these pieces of information. And I think the data that we have now will allow us to integrate this information. We could not do this 10 years ago. Thank you very much.
Thank you again.
Thank you.
Thank you so much.
The preceding program is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at med.stanford.edu.